welcome to the third lecture. In this lecture, I basically have two goals. One is to go through a little bit more theory, and then after that, there's a practical sections. Maybe three of you can form a group, and then you guys can try to build the model in the live sections. And then I will do it after the lecture. The lecture will be pretty short. I just want to see whether I think that it would be helpful if I can provide some guidance on how to build a neural network in person rather than in a group discussion format. So if you already know your classmate nearby, or maybe we can just find the closest people to form 3 people group, and then you guys can type the model together. So I just want to go through the basic, a little bit more ingredient about the constitutive modeling. We covered some basic last time. In this particular case, I would like to talk a few aspects of it that are actually relevant. The supervised learning that are actually the specific loss functions and the setup that are actually important for the elasticity problem. So again, you can see that extra. You can see the extra paper, the external word reading that could help you learn. Going back to that, so this class has 3 different goals. The goal to have a step-by-step setup of the supervised learning for elasticity. The mathematical background. I'm not going to talk about differential geometry or anything that super complicated, but I would like to give you some recipe or some necessary ingredient for you to think about how to write the constraint for the machine learning problem, and then I will talk about some particular physical constraints. So you can think about that. Half of it is half of the lecture is about just a review of container mechanics, just take out the old thing that apply to the new problem, and half of it is to how to approach the training. In fact, one thing that I haven't talked about, but actually very crucial, is the parameterizations. So for the same problem, if you're parameterizing the problem in a different way, we will get a completely different problem. I think if you have already taken the parasiticity class, you will find out that the constitutive law are written in the spectral decompositions. Okay, why is that? Okay, so there's a specific reason for that, and I will explore a little bit, but in the context of elasticity. Okay, we talked about the supervised learning problem last time for the elasticity. Again, we are actually trying to do something very simple, and you can also doing it by hand, which is actually given the input, produce the output, okay? And then in the simplest case, you can doing it with a polynomial or with a linear functions. But here, I'm actually want to talk about if I actually don't have any intuitions or any desire to actually write a specific form, can I actually come up with the functions that can actually fulfill the tasks of creating that functions. Okay, so in this lecture, for simplicity, I will just focus on the energy functional. But you can, but the basic principle is actually also apply if you actually don't want to write the energy functional. You can directly write a mapping that map the strain to the stress. Okay, so that's the general concept. We talked about it last time. Okay, so we have unknown target functions. Okay, and that target function is simply assumptions. Okay, in fact, we don't even know whether writing a function to mapping it is actually necessary, the right way to doing it, but we're assuming that there's a target functions that exists, which means that giving a string, you will get the stress, and then we would apply the hypothesis, and then we would actually talking about we would actually have the training label of the input. And then we're going to try to learn So here, what we actually, in this lecture, what we actually want to talk about is here, what are we trying to learn? Okay, so learning, in general, if you look at a lot of paper, that actually translate to just putting some mean square error and then make it to 0. But I would like to have a deeper dive onto how to formulating that. There's actually more than that for mechanics. If you think about it more carefully, there are lots of subtle things we need to consider, and there are lots of practical things we also need to consider. So this is actually what to learning algorithm. This lecture is about the constraint. We talk a little bit about the hyperparameter. I'm not an expert of tuning hyperparameter, but you can get a taste of how difficult it is to tune the hyperparameter. The easiest thing to control is actually the constraint out of all the ingredients. You think about the supervised learning problem. There's a data, there's a constraint, there's a hyperparameter. You can easily control the hyperparameter, but it's actually really hard to find the good hyperparameter. You probably already know that. And you oftentimes doesn't have access to additional data. Okay, data for solid mechanic is usually expensive. Okay, so what you actually end up with is to deal with the constraint. So how do I write the best constraint so that I can learn a little bit better? Okay, so and actually I'm curious that if you read the paper, most of the time that I just see a mean square error, right? So okay, you can think about the physics informed neural network as a special case of that supervised learning that have no data, just a constraint and the hyperparameter. Okay, I put some constraint, divergence of stress equal to 0 or whatever, and then I just hope to find the learn functions. Okay, but then we actually need to categorizing the constraint into different category. First of all, the data discrepancy. Okay, we have observed the real work, and then we all actually smaller scale simulations, maybe a molecular dynamic, maybe a discrete element. We get some data. Now we want to link it into a constitutive law. We want to minimizing that discrepancy. The discrepancy is actually very ambiguous. You need to define it in a very precise way. So what are the different choices we have? We're going to talk about that. We're going to talk about the constraint, what is the necessary, but not necessary, what is the necessary conditions for constitutive law to be considered correct. This actually applies to the hand graph model and the machine model, and then how to leverage the symmetry. Okay, so this is actually, if you don't know anything, if you don't want to design a neural network, all of those burden is actually relied on writing the right constraint. Okay, so writing the constraint properly is actually not a trivial task. Okay, so we're going to focus on that. Okay, so what are the constraints? Okay, so long story short, they are the necessary conditions for the model to be considered correct. I think that's obvious, right? Okay, in the image classifications, you would actually finding that the constraint is that you actually make the prediction on the new label. But on the physics problem, there are actually constraints more than just matching the data. You need to matching the data in the right sense. Okay, and how to define that sense? Okay, it's something that we already know in mechanics, and we can borrow some of the idea for the machine learning problem. Okay, so how do we enforce a constraint? Okay, so I'll just put one example. Let's say that I want the material to be film indifference. For example, if I actually write if I want to write the strength in a certain x, y, z coordinate system and then map it into stress in the same x, y, z system. Okay, now I want to represent the same strength in another x, y, z system. Okay, onto the same x, y, z system. Okay, if I actually rotate, because these systems are actually related by the rotation, right? If I rotate it back, can I actually get the same response? This is one example. And the simplest way to doing it is the following. You can explicitly putting this into the loss functions. What it means is the following. Okay, I'm actually predicting the stress, right? Okay, so let's say I predict the stress and then I try to minimizing that stress distance. Okay, let's, for the argument's sake, I just use the matrix norm. Okay, now I also want it to be to actually have the consistent results if I rotate the stress. Okay, so and then put the stress into the new stress algorithm. Maybe I just put point there. I would also get the same result. Okay, this is one example of rotating the data, and mathematically it's called equivariance. Okay, so you can actually, one possibility is that you can put this directly into the constraint. Another constraint that you may want to, you can put, well, there are many. Another one is actually you can also put the convexity there. You can, and then, or you can put other thing there. So the strategy one is to put all of them into the loss functions. Okay. So what is the drawback of putting it in the loss function is that the more thing you have, the harder to solve the optimization problem. You probably know. So if you actually have this, what you're giving, if you use the strategy one, what actually happens is that you're giving the optimization problem a multi-task optimization problem. So task one is to matching the predict stress with the actual stress that we regard as the ground truth, and stress two, and the task two is that while doing that, I actually want to want the equivariance. Okay. Now you can think about this. How many necessary conditions do you have to make it correct? There's a tons of them. Okay. Okay, let's say you have 100 of them. Actually, I don't think I can find 100. But in reality, I actually make a count is about, depends on what kind of symmetry you have. You have something about 8 to 10 different criteria. If you think about it, if you put it all there, it's going to be really hard to train. Okay, if you try it before in PIN, you know, you by the time you get a good boundary conditions, your divergence free of stress is actually way off. By the time you get this thing done, then the boundary condition is not fitting. Okay, so there's a loss of gradient conflict that could happen, and the more tasks you have in general, you're more actually having a task to the, you're more likely to actually create that conflict. Okay, so that makes the learning least feasible. When you think about a physical law or any constraint, there's only that three way. Okay. You understand what I'm saying? So the three way to impose a constraint, you have to pick some of them. And often for different type of constraint, you employ one of those strategy. Lecture, I will just focus on the brute force, which is actually put the loss functions. Okay, for the B-Wing neural network, there is a really active ongoing research, in particular for the Lie group and Lie algebra. I'm not leading this research. I'm not even able to follow that research that fast. So, but that may be something that we will cover in a later time. Okay, but then we will talk about the simplest strategy, which is actually to putting it into the loss functions. Okay, is that clear? Okay, so strategy two is very simple. Okay, now I'm actually already have the data. Okay, I have some stress strain curve. I just rotate the data, and then I actually create additional data for the machine to learn. Right? Is it easy enough to understand? Because the data actually fulfill the law. Okay, so if I put a lot of data it's possible that by by actually adding the additional data coming from the same source of data, I can actually able to achieve the rule implicitly. Okay, let me give the example. Say this is actually for rotations. I rotate it. I actually have the stress, but I actually only have a device that actually have a true triaxial compaction test. Okay. So I will have epsilon 1, epsilon 2, epsilon 3, and I have no diagonal term. Okay, I have a lot of those data, but then the problem is that those data, let's say the material is isotropic, I will only have diagonal term. Okay, but it doesn't mean that the material always in the principal stress. It's actually the tests you have that are in the principal axis, right? So what if I actually put this thing on the slope? Okay, now what will happen? Okay, it will be disaster, right? Why is that? Because all your label here is 0. All your label here is 0, isn't it? Okay, so you never get the chance to change off diagonal. And then the machine learning is actually, as we actually talk about in the classical way, the fit-for neural network is actually operate in a Euclidean space that doesn't have any geometry. So it won't work, okay? So there's an old way to doing it. Actually, in the 1994, when Professor Schaufer actually just come up with the idea that, okay, why don't I rotate the data? I actually create in the ordinary data, in the original real physical data set, I only have the principal axis. Okay, I map it here for coordination system X, Y, and Z. Okay, now I'm going to rotate this. Okay, so I'm going to create another set of labels that are actually already rotated. And then I put this both set of the data as an input. Okay, if I rotate it enough, eventually I cover the whole circle. Okay, so that is another choice. The problem of this choice, again, is that it's actually not that possible if you have a lot of choice, like rotations. How many rotations do I need? Okay, in 2D, you probably can managing it by keep rotating your data with one axis. In 2D, in 3D, you can already see that. Okay, so I have a very little amount of true data, and I rotate it so much. Then what would the neural network learn? Okay, so I think that this second choice I think is even worse than the first one in practice, just because of all the rule. But in some time it will work. Okay, if you really have so you actually struggle with those choice. Okay, and then because of that, there's a third choice that I actually then I was saying that if you have no idea, then just do this. But that would be the least doable strategy, okay? In this, popular by computer science people is that, okay, I don't really care about writing the multi-objective constraint, and I also don't want to add the data. I simply build in all the operations that are particular on the Lie group, okay? So I'll give you a very simple example. Those are actually more popular in the convolutional neural network. Okay, in this particular case, they would use spherical harmonic functions that are actually to build the solutions, and then they have the built-in SO3 behaviors, which mean that is invariant to the rotations. Okay, this is our convolutional neural network. In here, what is the choice we have? Okay, so in the case of the stress string behavior, we actually doesn't have a big matrix. We have a 3x3 matrix, or we have a column vector. So we can also build in the design. We can actually think about the operations that are always on the that are always obey the underlying physical rule, and so we don't have to explicitly enforce those rules. Okay, and we actually already did it, and this is actually the Lie group. The algebra. So I learned that when I was at Sandia, and then I make a presentations, and then the manager tell me that if you can choose to tell the truth, why are you lying? So but it turned out that it's actually Lie group, not Lie group. Okay, so just a chance to correct my pronunciation. So anyway, so we will talk about that. And then the lucky thing is that for writing the constitutive law, we don't need to think about the convolutional layer yet. Okay, so to operating that is very easy, and we already know that if you take the plasticity course, there's some trick to doing it. One way is that if you have the symmetry, okay, in particular, if you have an isotropic, then you can inherently build in something that are actually phi of the rotations, because you can actually predicting the epsilon 1, epsilon 2, epsilon 3 to the sigma 1, sigma 2, sigma 3. This is one choice, right? Okay. Why would that work for the SO3 is because no matter what you rotate your frame, okay, you have the same eigenvalues. Okay, so this is actually one choice. Okay, another way, but if you don't have symmetry, what you can do is the following. attaching the theme of the string and then predicting the spin. Okay, the spin between the principal axis of the string and the stress. Okay, because the string is an increment, so no matter how you rotate the string, it won't actually change. So there are multiple tricks to do that, and then we would actually talk about it. But okay, so we would need to be more specific about what we are going to put in. Okay, the first one is actually the discrepancy between the stress and strain. I think this is actually clear. Okay, so I think I talked about it in the last lecture. We can actually minimizing the energy discrepancy if you have those data. You can also minimizing the energy and then the stress predictions, because the stress is actually the derivative of the stress. Geometrically, what you have is the following. Okay, let's say you have a string and then you have an energy, and then the energy may, I don't know, how does it look like, maybe something like that. Okay, then the slope of it, okay, will give you the stress. And if you actually take the derivative, you would get another curve. I don't know how would it look like. So positive, and then it changes you. Anyway, maybe. So these two may not be consistent, but if you actually take the tangents, then you will get the tangential stiffness. Okay, for different points, you get a different tangential stiffness. It's actually not a constant unless the underlying quantity law is linear. Okay, so if you actually want to do the H1 norm, then you need to include this. If you do the H2 norm, you include more. In principle, you can include however degree you want. You can even take the tan derivative, but then you need to question that, does it really have that degree of continuity? Maybe not, right? So then you don't need it. Another interesting thing that very interesting in matching this is that what norm we use. So here we use a Soberlin norm, so each of the term is actually itself a L2 norm for the corresponding respective measure, but you can actually use different norm, and different norm would actually affect the optimization problem. You're giving the optimization problem a different sense of the distance, and the sense of the distance is crucial. And one final aspect that are actually interesting is the following. You have three set of a label, okay? You don't have to use all set of the label to actually recover the energy functional. In fact, what we actually try is that if you only have the stress, you can also back extrapolate this and this, right? Because let's say for consider 1D problem, okay? If I just want to draw a straight line and I know this point, okay? And then I know this point, maybe I can already draw the straight line, so I don't really need the gradient. But then although I can say that this is actually true. But let's give another example. If I have this point and I know the slope has to be a certain number, I can also draw a straight line, isn't it? Okay, so or actually in some sense, if I know there's a curve and then it starts here, and then I have all the slope available, all the slope informations, I can also draw the curve, okay? And that is also an important thing to consider, because think about that, the string is actually a scalar, so basically you're giving a tensor, and then that would actually map it into you have R3 times R3, and then you basically map it into a positive number, maybe including 0. But then in the stress, the stress is already a second order tensor, and then for the stiffness, you actually have a fourth order tensor. So you can think about it, the higher the term, the more component you have. And the thing is the following: if you actually have a lot of data, that calculation itself, that loss function calculation itself is also going to be slowed down. Okay, so there are multiple ways to do it. Some people would actually did not compute the entire CEE316 but actually stochastically sample the tangents, because you don't actually need to check everything. You just need to check some of them. If some of them are actually really terrible, you would actually detect it. Okay, so, and also another thing to actually remember is that these things become harder and harder when we're increasing the dimensionality. Okay, so the higher the dimension it is, the less feasible to you using this classical norm. Now, how to do it with the non-classical norm, we will talk about it at the how to do it in a very high dimensions, we'll talk about it at the end of the lecture. Okay, so but then the key here is that, or the thing that I think will be useful is that whatever data you can measure, you need to find a way to actually incorporating it and then put the right norm to it. So the criteria one is actually matching the physical measure. Okay, there are other special cases such as if you have the digital image correlations, you have the spatial results, but we won't cover that in this lecture, but maybe later we will actually revisit this. Okay, if you do the first term better, if I do this term better, I may sacrifice the second term. Okay, but in general, we talked about that in the last lecture. So here, what I actually want to emphasize is that there are two possibilities when you actually add the additional term. One is that you have the gradient convex, which means that if you actually, because I think the underlying reason is that the stress is coming from the derivative of the energy, and then the tangent is coming from the derivative of the stress, it kind of helps you to draw the whole energy functional, so I don't encounter the energy, the gradient convex here. Okay, and this is a real applications on the MD simulations. As you can see here, you can actually implement the informations, and in some case, you can also you can actually also deal with different amount of the data. So here, I did not use any energy functional except that I know that there's a reference. If I don't have deformation, the energy is 0. Okay, and then everything is a stress, and we cover the energy functional. Okay, so in a sense, in the MSE, you are actually controlling the matching of the point. Okay, but then the gradient term is actually to help you to control the slope. Okay, so if you control the slope and control the point, very likely you will get something closer to the true defined. But then that relies on you really actually write the criteria properly. You understand what I mean? Because for the L2 norm, there is no difference of how the gradient is. Okay, so now I'm going to move on to other type of constraint. I need to talk a little bit about the container mechanics. I would actually consider a very specific problem that are actually not necessarily the best choice, just to elucidate the idea. Consider that I actually have reference configurations and actually a deformed configurations like the potato we saw in the last lecture, so that so that I have a mapping. Okay, if I take the first derivative of this, I would actually get the deformation gradient. Okay, now this is actually the interesting thing on that is that if I actually define the energy, if I seeing a material that are getting compressed or actually shear, okay, from this angle, okay, I'm looking at it right now. Let me give some eyebrows. Okay, okay, just to make it look like human. Okay, and then I look at it here. Okay. Okay, so I'm actually rotating my perceptions, my observer 1, observer 2. Okay, what happened to the amount of energy stored for these two persons? I mean, I'm not talking about relative generalized or special relativity. I'm talking about the Newtonian world. Okay, so if you and I both looking at the same thing and I'm rotating my head a little bit, and then that thing is actually stored, if I say that thing is storing the 1 joule of energy, okay, 1 kilojoule of energy, what would be your answer? It will be the same, right? Okay, so that's the interesting thing. If you do in machine learning, it will give you a different answer just because it doesn't know that it has to be frame indifferent. So one brutal way to doing it is to actually implicitly put it into the functions. Okay, so here the Q is actually a rotation tensor. If you actually remember in undergrad, rotation tensor is actually belong to special orthogonal group of n, and n is the dimensions. What is special orthogonal group is actually a very special tensor that actually, if you where the inverse is actually equal to the transpose, this is one criteria. Criteria 2 is that the determinant of Q is actually always equal to 1, not minus 1. Okay, only positive 1. Okay, that would be any rotation. So so what I mean is that observer 1, I will actually have x, y, and z. Observer 2, I will have another x, y, and z, but I would actually add that additional thing into the loss functions to ensure that if I actually rotate my head, I will actually get the same amount of energy for the predictions, and so does the same stress, and so does the same tangent. Okay, so this is actually called the film invariance loss functions that you can actually add it to actually ensure the correctness. Okay, and you can see the result. This is two results. Without doing this, it's actually not that bad. So sometimes you don't really need it. But if you're enforcing that loss functions explicitly, you can actually make sure that you can actually eliminate the annoying fact that if you rotate your frame, you get a slightly different stress predictions. Okay, which I don't know. I think it bothered me a lot. Maybe I don't know whether it bothered other people. But then your material model is actually more could be deployed for any frame. Okay, if you don't do that, then what you actually need to do is to remember the frame that you train your model, and then if you're just rotating it after you actually get the predictions. Okay, which is actually fine. The problem is that most of the people forget where they put their frame. Okay, so a lot like the previous one, except that the Q is now not putting it in the first index, but on the second. Okay, another one which I actually need to write it more carefully is that I'm sorry, I did write it correctly. It's actually the symmetry loss functions. What is a symmetry loss function? It's an index. Okay, so so if I have a mapping that are actually on X and then actually mapping from this, okay, so what actually happened is that there's a J here and there's a I here, sorry, there's a J here and there's actually a J here, but they are actually, the two bases are actually not identical. Okay, in the previous one, we're actually rotating, so if I linearizing these actions, this thing, I actually would have the change of the, I would actually have the deformation gradient, and the deformation gradient would actually have one tensor that are in the current configurations, and then another one that are actually on the reference configuration that are in capital line, and then Jx is actually the reference configurations. Now this Q is actually putting in the reference configurations, and if you actually, I won't go through the math here, I just tell you this is necessary in the sense that this is dealing with symmetry. Okay, so for isotropic material, this is actually simple. What it means is that Q would be anything related to SO3. If you're rotating it in any, what it means is that if a material is isotropic and then I apply the amount of this, let's say sigma 1 here and sigma 2 here, and then I rotate, and then I consider these two cases. Sigma 1 is here, sigma 2 is here. Okay, first of all, these two cases will produce a different stress tensor, but then if you rotate it back to the 90 degree, you will get the consistent results. Okay, on the other hand, if I actually have a layer material, okay, I would actually get a different response. However, if I actually rotating it on the frame, then I would actually have isotropic behavior. So what it means is that for isotropic material, Q is anything in the SO3 group. For the transverse isotropic material, Q is actually in SO2 group. Okay, why is that? Because you have an isotropic plane that are actually independent of the amount of the shear, but this direction and this direction are different. Okay, And then this, you have to define the particular rotations. So the rotation would not be any arbitrary SO3, but the SO3 subset. And for crystal, you have a lot of these rotation group, monoclinic, etc., that if you want to model crystal, this become very important. Okay, you just need to find out the corresponding subgroup in the SO3 that you should obey the symmetry. Symmetry need to be explicitly implemented in our numerical experiment. You can see that. Well, I mean, it depends on what you define as an Euler. If you don't explicitly enforcing it, you can actually rotate the data. But in general, it's really hard to implicitly learn the rule. So this could be the one clean way is to put that additional loss function there. Okay, so which I'm surprised most of the people did not do. So, okay, so. But this could be important. Another choice is to simply change the parameterizations. As we say before, in the isotropy case, you may not put the f as the input anyway. So what are you going to do? You typically put the determinant of f as one of the input to write the energy functional, and then maybe you use the first and second invariants. If it's first, second, and third invariants to write the elasticity model. That is also another way to actually doing that. So it depends on whether you want to leverage the symmetry to reduce the dimensions or you want to add the constraint. How to mention that, measure that, we may use L2 norm. Okay, so far so good. Okay, so then there's another conditions that actually would be interesting to talk about. This is called growth conditions. So that goes to two things. If the deformation gradient becomes 0, so what it means is that if a finite volume object become a point, it will take infinite amount of energy. So this is a theoretical container mechanics stuff. In real life, you won't have an elastic behavior that allow you to collapse volume into a point. But if you write an elastic material, you may notice that your predictor you may still need an elastic strength range that cover that unimaginary thing because you need to do it in the return mapping. You need to have a tri-stress that assume everything is elastic. Okay, so this is what happened. This is actually a real training data. The data is actually roughly here, which is actually pretty cool. And but then this part is image have no data. Okay. So this is actually a dangerous use of the neural network, and then you can actually seeing that if I don't do an out of sample training, I won't discover that the growth condition doesn't meet. Okay, so how do I meet the growth condition is that it has to go to infinite. Okay, but how to enforce something that go to infinite? Okay, so this is actually also an interesting thing. I think there's a work that actually do with that, maybe with the Lie algebra. Or something, or implicitly doing that, I have, on top of my head, I don't have any idea how to write it mathematically. Do you guys have any idea? You can put a very large number, but how large is large, right? You see what I mean? You can say that if a determinant of f, well, there's a two difficulty there. I think approaching 0 is you can probably guess a very small number, and infinite you can guess a very large number, but is it necessarily a good choice? Okay, it may have a unknown consequence. So anyway, but the growth condition is something that a lot of people also ignore, but are very important if you actually want to predict something really wild. Okay, and that doesn't necessarily only apply to the volume. It could also apply to the directoric stress as well. I mean. Well, the return stress maybe not, because you can assuming that at some point you probably mathematically it should go straight line. Okay, but at least for volume, this is a well-known fact that that could lead to a problem if it doesn't. The same thing for if the deformation f is actually infinite, and your energy should also go to infinite. I think that's also obvious, right? Not explicitly, and then okay, so. Another thing that the last thing we also need to check, and this is the hardest thing, so to check is the strong ellipticity. So what does that mean for strong ellipticity is the following. Okay, so for a stress string responded nonlinear, the second derivative in the 1D case, the second derivative is actually the stiffness, and there's a tangential stiffness. what we actually require is the following. If we propagate a wave propagation problem, we need the acoustic tensor in the small string would be the normal vector times c times the normal vector. This one has to be non-singular. Okay, so if the acoustic tensor is actually singular, then you cannot capture. Then your elasticity problem will have some problem in the sense that the wave speed is actually vanish. Okay, so this could be done by checking, but then the problem is that in order to check, you have to check all the angle. So n is a normal vector. Okay, it could be. The problem is that imagine that I want to make sure what you actually want is to make sure determinant of A is actually greater than 0, okay? But then there's many different A, there's not one tangent. You need to, then what actually you need to do is to find the minimum of the determinant A by finding the right N. Okay, so that become a harder problem. So this is one example. You need to, when we actually enforcing the elasticity, but when you add the loss functions, you actually it's actually not that difficult. You simply want to check whether the smallest determinant of A for given C is actually greater than 0. The problem is that you have to rotating the angle. You have to create a normal vector by keep sampling it, and you need to, out of all the possibility orientation, you need to find the minimized N for that C. Okay, and then C is actually changing for each different point. So the evaluations of the strong elasticity check is going to be very expensive. Okay, do you guys get the idea? Okay, all the other thing, I have the stress, I have the strain, I just compute the norm, and then or I check the criteria with mathematical expressions. Okay, this last one is harder to enforce because you don't really have a mathematical expression to this. And then another difficulty to check this is that if you plot the landscape of the determinant of the acoustic tensor along the angle, along the normal vector, it usually have multiple minimizer, and you need to reach the global minimizer in order to enforcing the acoustic tensor. To actually find the true minimal acoustic tensor. So this make it very difficult. But what you can also do is that if you don't enforcing it, you can actually check how much error you get. Okay, if you actually for given C, you would actually have a landscape like that by rotating these two angles. You just locate the minimizer and then you check whether you would actually violating the acoustic tensor being 0. If it does become 0 or it become negative, then what you may actually see is some unstable behavior for your learned model. Unfortunately, this is also pretty common if you don't train it properly and using many exotic activation function. This is actually what you can get. So this is actually also important to check. Okay, so but this is actually only coming from kinetic mechanics. Nothing special about machine learning at all. And yeah, if you work on constitutive model before, it's kind of like a common sense. Okay, so far so good. Okay. All the different criteria, okay, but then, okay, so now we go to the second questions, how to measure the error or the loss functions. Okay, we're talking about, in fact, the way to measure the error is related to the physical property. Okay, does that make sense? Okay, so I'll give you an example. If I want to measure the stress, or if I actually write a predictor that given the stress, I would actually predict the deformation gradient. Okay, I'm not saying that it makes sense. I'm just saying that just for the argument's sake. Okay, so how do I actually going to measure the error? Okay, I have multiple choice again. I can actually compute ij and then check the component one by one. Okay, that's one choice. Another way to measure the error is that I do a polar decompositions. Okay, and then I check individually how close is rotations and how close is the principal stress. I separately measure that and I combine that. Okay, and then actually the interesting thing is that there are infinite, or not infinite, there are many different ways to do it, and then for different norms, for different Euler measure that you import, you get a completely different model, because your perceptions of actually being good is actually completely different. And more accurately, in principle, if the Euler is 0, you get almost the same behavior for all of different measures, but if it's not, then if you don't reach the absolute 0, then the Euler will have a completely different meaning and you get different attribute or behavior. This is actually what I will want to talk about. Now, what I'm going to do is to talk about all the loss functions in PyTorch one by one. No, I'm just kidding. I'm not going to do that. It will be completely meaningless. You can read the manual, right? Okay, so I'm not going to talk about that, but this is just to give you the idea that all of them have been used for different tasks. Okay, if you look at the manual, you will find that some of them are used for image classification. Some of them are actually used for time series predictions, and some of them are used for vector predictions. Nothing is for mechanics, I guess, because mechanics doesn't earn that much money these days. So it's no specific thing. So, but I guess it created a room for us to customize and then think about the loss. Okay, the loss is related to how do we measure how good it is for the constraint. Does that make sense? And then how you define the loss actually matter. Okay, so first I would like to talk about that questions. I think if you're a Stanford student, you probably are not that poor, and then you may have traveled between Australia and South America before. I'm not sure. Okay, I'm just making political incorrect assumptions. Okay, so if you actually sit in, and I suppose that you're not going to take the low economy flight, you're going to take the regular United American or whatever, that actually have a computer, that have a screen. If you have a screen, you will see a map that look like that. Okay, so what is the problem of this map? Okay, so this is actually the pilot broadcasting and saying that I'm going to travel here from one nice city for another city for your vacations. Okay, and then he's saying that the red curve is actually the shortest path. Okay, so what is the problem here? It doesn't look like it's the shortest path, right? Isn't it? Or why is that? Okay, the shortest path is supposed to be a straight line here, right? Okay, so I should cross the South Pacific Oceans and then not going south, and okay, but why would you do all the travel doing that? Okay, so if you're from China, you know you need to go to Alaska all the way, going back. You may actually get pretty close to Tokyo, and then you go down. So why do you need to do that? Okay, well, I mean, it's not for political reason. Okay, it's not because you want to visit Alaska and avoid Russia or something like that. Okay, it's for geometric reasons. Why is that? Yes.
Are we taking into account the fact that the Earth is spherical and we're using?
Yeah, exactly. Okay, so this is actually the beautiful idea, because if you actually curve this map, and then put it into the globe, you will find out that this is actually the shortest distance. Okay, but then that shortest distance is actually different than the shortest distance when it becomes flat. Okay, why is that? Okay, yes.
Because if you map for spherical coordinates in the Euclidean space, there's always going to be a distortion per
yeah, exactly. Yeah, so exactly. In fact, there's a paper saying that there's no way you can actually deform a 3D surface onto a 2D surface without distortions. Okay, that has been proven. And that's why all the publisher, when they publish the map in 2D, they always have some distortion. Maybe they use some funny shape to get to minimizing the distortions. Okay, but what does it have to do with the mechanics? Okay, what does it have to do? It actually have a lot of things to do with it. Okay, just think about the deformation gradient. If I'm rotating it, if I'm splitting it, do a polar decompositions, I will have the rotation, right? Okay, what is rotations? Okay, so I have a ball in the 2D. I actually have the center. I can rotate it, whatever I want. And then the determinant is equal to 1. That means the distance is never changed. Okay, so I'm actually also on the growth for all the mechanics problem. If I think about the spin, the elastic spin or the plastic spin. Okay, so so actually another important observation we want to talk about is that, okay, this green line and this blue line seems to have very different distance, right? Okay, but let's give another example. If I go from Sydney to Melbourne, okay, and you use a map that is flat, it's actually not that bad, right? Okay, what does it tell you is that, yes?
I was going to guess it's a manifold, so it's locally equivalent to Euclidean space.
Oh yeah, you already know that. That's what I think. Yeah. The reason is that this earlier is more apparent for when the data are actually very sparse. When they are close, it doesn't really matter. Okay, so the loss functions, to how important it is also depends on how much data, what is the density of the data. Unfortunately, for mechanics, it's not like a Facebook, you have a way to mine the data. The data are always almost very sparse, or more accurately, you will think about the following analog. In general, what actually you want is actually the data that cover all the space with a loss of density. Okay, this is actually what you want, and that would make the learning very easy. The thing that what you actually may have is something like this. Okay, it's not just sparse, but it's not about the sparse, but you have a very dense states locally, but globally it could be you have some neighborhood that are actually very far away. Why is that? Okay, because of the physical instrument that you have to model to actually measure the string. Okay, you have a uniaxial test, you have a shear test, but you don't have something in between or something like that. So inherently, the data are not. It's not necessary distribute evenly. And even if you actually think about the distribution, is also related to how we're parameterizing the space. If you actually do it in piping, okay, for the stress, you may actually equally define it along the angle of the on the piping. That would be different than you equally spacing the component. Okay, you see what I mean? So anyway, so there are a few different concepts to use. Is that presumably we want to associate the loss function with a meaningful distance. Okay. And the meaningful distance depends on the physical quality you want to build for your constitutive law. Okay, do you get the message? Okay. Okay, so the thing is that the distance and norms the same thing. If you actually you look at Mathematica or ChatGPT in this day, you would find that they are the same thing, only in the Euclidean geometry, which is actually a flat space. Okay, if you actually have a 2D R2 space, okay, you can simply use the norm as a distance, there's no problem, okay? However, if you actually deal with something that are nonlinear or have some geometry, then the distance and the norm actually not becoming the same thing. Let's do a SO2 example. Let's consider a circle, okay? The distance between this point and this point is actually here. Okay, and to measure that is actually not that is actually not that difficult, but the thing is that this is actually different than measure it with, maybe I take a larger chunk. Okay, let's say here to here. Okay, to measure the distance between the green line is actually different than measure it in the blue line. Okay, is it obvious? Now I want to minimizing the distance. So my perspective is very important. Should I do this or should I do this? Okay, so in practice, 99% of people are using the blue line, which is, sorry, I shouldn't say that. I don't know the 99%, maybe 98 or 95. But I would say the following, in general, that can lead to some funny behavior, and they are actually stemming from the fact that when you try to minimizing the intermediate model are actually not even in the group. Okay, so you violate the property. I'll give you an example. If you actually try to change something and then you do a spectral decompositions at the middle, the rotation would not be a rotation anymore. It will actually have distortions. The linear algebra course, or let's go back to that. Okay, again, in a fact space, you keep the norm, and then the norm will be a good measure for the distance. Like a 2 point in here and here is actually perfectly legit. You can also actually, assuming that if things are linear, you can actually also using the matrix norm to actually measure the distance. And then again, there are different matrix norm. And if you actually equip using a different norm as your perspective, you get a different loss functions. Okay, so how do we resolve that? Okay, then I'm not going to talk about the group theory. I'm not personally an expert of that. I know the very basic of it. So, but I just want to teach you the very basic so that you can using it the very basic. Okay, the idea is that either you operate in the group or you actually operate in the Lie algebra. So the Lie algebra, like what we discussed before, is actually the tangentials a space of the Lie group. And what is the nice thing about anything tangential is that by the very definition, the tangential behavior is actually Euclidean. Okay. So we're actually using it a lot, okay? So for rotations in continuum mechanics, are we actually dealing with the rotation directly in the astrophere a lot? Okay, so we actually don't, right? What do we deal with when we write a constitutive law? We actually deal with the spin, right? Okay, so what is the difference between the rotation and the spin? Okay, what is the difference? So the rotations is actually astrophere group, so that means that you have this behavior. Okay, which is actually not so easy to enforce when you also try to interpolate something. But spin tensor are much easier to deal with. Why is that? Because the spin tensor is simply a skew symmetric tensor. Okay, a skew symmetric tensor is that the of component A, B, C, and then that would be minus A, minus B, minus C. They actually, the transport of them cancel out each other. Okay, so they are both rotations. Okay, but then the spin, in fact, is actually the Lie algebra of the Lie group rotations. Okay, but what is the beauty of the skew symmetric tensor? Why is it easier to deal with? Is that, let's say I have a skew symmetric tensor, let me call it a small r, and then they are actually, so in a sign convention, the small letter are actually corresponding to the Lie algebra. The capital letter are actually corresponding to the group. Let's say the rotation is in the Lie algebra, which is a skew symmetric tensor. If I add two skew symmetric tensor, I would actually get a new skew symmetric tensor, isn't it? Okay, it won't suddenly become symmetric. Okay, it could become, you see what I mean? You can cancel it out, but then you will always be on the Lie algebra. Okay, now if you're doing it, if I rotation 1, I add a rotation 2, do I get a rotations? Okay, I would not. Okay, you're actually going to get distorted because actually I'm mapping it outside. Now the key here is the following: how do I map between these two worlds? Okay, so the trick here is to do the following. I have a physical quality that are in the Lie group. I actually don't want to measure the difference in the Lie group, but I want to measure it in the Lie algebra that are actually Euclidean locally, okay? And then this is actually the trick that lots of people use to actually create group predictions. And mechanics is actually also in group, okay? So this is some key idea. So we just want to show something related to the group. Okay, there are many group, even the positive real number is actually a group, and then they corresponding to the Lie algebra that are just real number. A special linear group, okay, so it's actually a group that the determinant is actually not equal to 0. So obviously that the deformations gradient is actually a linear group. It's actually belong to a gradient general linear group, although it's actually not, although there's a group element that are actually not a deformation gradient. and they're corresponding to n by n matrix that doesn't have that property. Okay, and then there are more things. That identity component group is actually the one that requires this to be greater than 0, so it cannot have any flip-flop on the. You cannot have these 2 points and then just mapping it. You see what I mean? You cannot have flip the coordinate. So this would be just be the property of the deformation gradient. Okay, and then there are special linear group that are actually also quite often in container mechanics. What is special linear group? Kinematically, is the determinant of A equals to 1. That means they preserve the volume, and that would be the isochoric deformations. Any deformation that doesn't change the volume would belong to the a special linear group, and then there would be an orthogonal group, special orthogonal group, and there would be symplectic group, symplectic group. So there's a one faculty member that are actually expert on the symplectic group. Actually, so I won't talk about that. I think that I'm scared when I talk about. Sorry, I think. Sorry for the insider joke, I think. But if you're interested, you would know the answer. A symplectic group. Okay, search it. Okay, so the key is how do you actually connect it? Yeah, so that tests your container mechanics knowledge. How do you connect it? How do you get a spin out of 2 rotations? Okay, in classical container mechanics course, how do you do it? Okay, so I would say the majority of that relate to logarithmic and explanation mapping. So what do? You may actually remember in your undergrad class, you have a curve that are actually very nonlinear, and you don't want to model the nonlinear behavior. What you're going to do? Okay, you just take the log of it, right? Okay, what happened to the log? No matter how nonlinear it is, after the log it looks like linear, right? It may not be exactly linear, but if you have a point that looks like that, it actually becomes much more linear, right? Okay, so the majority of them are actually done from logarithmic to map it from the Lie group to the Lie algebra, and the exponential map that map you back, give you back the curve. Okay, so the underlying intuition is that if I do a log, then the thing will actually become flat, and then if I do the exponential thing on this curve, it will become curvy again, right? So it will actually get back the exact geometry. Okay, so there are explicit way to actually linking. For example, another thing I don't have time to discover is the damage. If you're actually modeling the damage is a material parameter to actually show the degradation of the energy, and it could be 0 to 1. Okay, but then the interesting part is that it cannot be negative. So if you do it in the Euclidean group, when you do the learning, you may actually get the negative values. That would a negative damage probably doesn't make sense, or a damage that a degradation that are minor probably doesn't make sense in most cases. And then I just want to give some example, and then we'll go to the tutorial. Let's consider the following. Okay, let's consider axis, the parametric space that actually contain -1, 1, 0, and 2. Okay, I have 2 ground truth. Actually, one is in -1, one is in 1. Okay, and then I want to do interpolations on 0, and I want to do extrapolations at 2. Okay, so Z1 is here, C2 is here, and then what I want to predict is actually these 2 numbers. Okay, I'm just giving you some example that I already know. Actually, this is actually coming from the paper from our colleague Alejandro Mota, that I'm actually also a co-author. But actually, let's consider that this is actually the special linear group, like a deformation gradient. The determinant of it actually is supposed to be positive. Okay, so now I have that C0 and C1. I try to interpret what is at the middle. Okay, what is the easiest way to do it? Okay, in the Euclidean space, I have the component, right? okay? So the easiest way is just to take the average, right? Because this distance is actually 1, this distance is 1. If I actually want to predict what happened at z0, I just need to take the average component by component, right? Does that make sense? Okay, and this is what you get. So 2, 2 actually is 2, 0, 0 is 0, 4 plus 0 divided by 2 is actually 2, right? The 2, 2 is actually 2. Okay, now after that, this is actually the matrix. 2, 0, 2, 2, 0, 2, 2, 0, 2. Okay, that's right, this is actually 2. Now, the interesting thing is that if you actually compute the determinant of it, what is it? Actually, that would be 2 times 2 times 2 minus 2 times 2 times 2, right? Is it? Is it? I think so. Right? Is it? I think so. Anyway, so what happened to this? Is it still in the general linear group that required the determinant to be larger than 0? Okay, so it would not belong to the linear group. If you do the explanations, that would be even worse. Well, not necessarily even worse. You may actually accidentally be there, but you may also not be there. The thing that most obvious is for the rotations. So in this case, you actually, the rotations, these two, obviously, if you're checking it, the transpose of it are equal to the inverse. But then if you actually add these two terms together, you get this matrix, and this matrix is actually not the SOV group. You can actually check the determinant of it, or you can actually see whether the inverse is equal to the transpose, and so does this one. Okay. See here, you get 0.5 for the component. The magnitude is always 0.5. This is always 2. You do that. So if you do it in the Lie algebra for the same matrix, you will get a different number. Okay, this is actually very important. But here you get a different number. Okay, so why is that? Because you are operating in the Lie algebra, not in the thing. So indirectly, you deal with the nonlinearity in the linear interpretations, but you are not actually doing the average in the Euclidean sense. You see what I mean? Okay, so what I mean is the following. In the SO2 case, if I actually have 2 points, I take the average, I will get here, right? Okay, versus if I actually know the geometry, I take the average, the distance is identical, I will land it here, right, isn't it? So this is the underlying geometry, okay? So there are other rules that, okay, so this is just the answer of how to do it in the SO3 group. You can actually finding that one advice I want to give it to you and to all of the students is that log of a second order tensor is not equal to the log of each component. Okay, so don't do that. Okay, so you can actually get the logarithmic either by spectral method or by infinite series. We would actually also talk about it in the next lecture. This is very technical, so I would actually omit those details. This is actually a spectral way to do that. And also one interesting thing I would like to point out is that one important thing is that there are actually a benefit in the SO3 in the group, not on the algebra, is that in the algebra that could be singularity, while in the group you don't. Okay, so now what is the implication of the loss functions? Okay, also require. Okay, I'll just give some example. Okay, this is actually just 2 rotations that we want to predict. I want to actually predict an anisotropic elasticity, anisotropic plasticity. So given a strain, I will get a stress, but the strain and stress are not sharing the eigenvector. The eigenvector are actually rotation from each other. I want to predict that rotations. Okay, so I knowing that. Okay, I know that. So eigenvector are actually orthogonal to each other. So if you group 3 orthogonal vector and put it into a column, it forms a rotations. Okay. Now I have one set of the eigenvector for the string, another one for the stress, and I'm only doing in spot deformation. So the left eigenvector and the right eigenvector are identical. Now I have two sets of eigenvector. I just need to actually find out what is the spin. And then if I actually get a complete match, the spin would be 0. There is no spin need. Okay, but if I actually the prediction is very far away in the sense of the rotations, I will have a lot of spin. Okay, so there's a paper also in the external reading. There are admissible matrix that are actually all there, that are actually example. There are more than that. But the interesting thing is that I would ask you to try it later on in here is that try to actually using this as a loss function to see what you get. Okay, you will get a different stress prediction just by actually enforcing this perspective on the rotation part. Well, the first one is pretty easy. I actually have Euler angle, and I just compare in that eigenvector what is the free Euler angle, what is the discrepancy of the Euler angle. Okay, there's a limitation on that. In that case, is that if you use the Euler angle, imagine that you rotate it by 380. Okay, you can expressing the stress in a different way. You just need to change the magnitude from positive to negative, right? So there could be some consistent issue that you need to, once you compute the eigenvector, you need to sort it out and you need to pair them carefully. Another limitations of using the Euler angle is when your stress is isotropic. Okay, when the stress is isotropic, that means that all the eigenvectors are identical. And because all the eigenvectors are identical, but your eigenvector is still spinning in the, still span the S, still spanning the entire R3 space, what will happen is that the eigenvector attached to an eigenvalue can easily rotate it by 90 degrees. Okay, so in the Euler angle measure, that is actually the problem. You may easily get a 90-degree measure thinking that is really bad, but in fact it's just because of the eigenvalue decomposition is actually not easy to conduct. Another one is a probability tax. What we actually, probability test, not the tax. Okay, I think we all hate tax, but test, I'm not so sure. So this is actually to check whether it looks like rotations. Okay, I think that would look like a rotation is that when R2 is simply the inverse of the R1, right? If the two rotations are identical, okay, they would actually, if two rotations are actually identical, then I should have this behavior, right? Because the transpose of the, because I know that R1T would be actually equals to R1 R transpose, R1 minus 1, and then I will get identity, right? So this is called identity test. If R1 equals to R2, I will get the identity and the whole thing will become 0. Okay, so this is actually another way to measure the distance. Finally, this is actually the Lie algebra. I just take the log of it, of these compositions, and then I see whether I get any spin. Okay, so whether the spin is actually matched. Again, all of them would actually work in some sense, but they behave very differently when you don't have enough data and the data is very sparse. Okay, why is that? Just go back to the original problem. If you don't have that much data, then the norm you use to measure, then your distance matrix would actually govern how the learn function will look like. Okay, you see what I mean? When you have a lot of data, you would actually find out that if I actually pick a different norm, I actually more or less get the same learn function because I just have so many control points. I don't have that much freedom to draw the to get the learn function. When you don't have enough data, then those details become playing an important role. This is very specific for mechanics or for physics that have property specific learning. Okay, so I would like to talk about the last thing, and this is actually for high dimensions, and then I will stop. Again, I think I talked too much again, but I think we will have the lab sections here, and then if not, then in the next lecture I will really try to finish the lab. In the exercise that we actually talk about is related to that concept. We remember that I think that Ming actually draw the figure about the circle become ellipsoidal and then rotated. So this is actually the underlying idea. I want to talk about the last thing is actually related to very high dimensional case. Imagine that I'm actually trying to obtain the measure for some very high dimensional elasticity. Maybe the elasticity that take all the deformations gradient component, or maybe something that are micropolar or micromorphic, okay? So in what we actually did before, we actually fixed one axis and we have some point, okay? And then we try to map it to y, and then here, and then I compare with the ground truth. Okay, so the pair that are used to measure the Euler is actually fixed. Okay, I have a ground truth point set. I have a ground truth, usually a point cloud that is discrete, and then I have a continuous set that I generate by actually locating the same the basis of an x component, and then I map it to y, and then I just compare the discrepancy on y, right? Okay. But in general, this is actually not effective in high dimension, where imagine that you in the 1D, you draw a straight line, you only need 2 points. In 3D, you need 3. If you actually have 27 dimensions, you actually need actually 27 points to just draw a hyperplane that are actually straight line, that are actually just straight in some sense. So we need to use a different method, and that is actually related to the optimal transport. I won't talk about too much detail. I just want to talk about these two terms and then the basic idea. And then in the later, I will have one lecture just dedicated to that. This is very important to denoising. Okay, this is actually why I want to talk about it. Okay, so I just want to talk about a little bit of history. This problem is coming from World War I, where people want to dig a lot of hole with a lot of earth, and then I want to merge the earth to the hole that I need to dig. You know, in World War I, they build a lot of tunnel. Okay, then you need to remove the material and you need to put it into the other side. So the idea is the following. I actually need to, let's say I actually have the source that are actually in a wet ball, and I want to find out a pen, and I'm actually not particularly marry one wet ball to the blue ball, but I simply want to divide a pen to actually minimizing the cost to make it as cheap as possible, so that I can actually fit this. I can actually put all the mass of the earth to the right locations. So the right way to doing it is the following. The minimum cost, the cost is actually the minimum cost that we actually need to consider is to divide a pen such that I can actually find out what is the optimal way to do each of the matching, so that I can actually move something as using as least effort as possible. So this is actually called the Monge optimal matching problem. As you can see, it's not very effective, because if you have a lot of pawn, let me take one pawn for example. Let's say I want to deal with this pawn. I want to check whether what is the best one. In your eyes, you know probably this neighbor, right? But in a computer, you need to search for all of them and then measure the distance, and you know that this is actually the right nodes, and you're repeating that. Okay, this is actually too slow. So people are thinking about this because they're thinking that if I actually want to measure the Euler, the minimum cost is actually a very good measure. If I actually divide the optimal transport pen, and that pen is associated with a cost, I can use that cost as a measure of discrepancy. And the reason that is actually getting exciting is that the idea is that it will work on manifold and other geometry that are not necessarily flat. Okay. So there's a lot of work, but I just want to give you some taste on that. So let's say I have a travel pen. That travel pen is going to be like this. I just have 4 matrix. I basically will generate a permutation matrix that map the node 1 to 4, node 2 to 3, node 3 to 2, node 4 to 1. Okay. and then after that, I will measure the length of this term, and then I sum it up. So the length of this term is actually basically this, and then I would actually get a sense of the distance. Okay, you get the idea. So if the two, this could be used to measure the error, because if I have a two curve that are identical, and then I pick point to it, the minimum cost will be 0, right? You see what I mean? If the red and the blue dot are in the same positions, then the minimum cost will simply 0, isn't it? Okay, so that could be a good matrix for the point cloud to point cloud comparisons. However, that will still be very inefficient. It doesn't help solve the problem. And also, if I actually doing exactly like this, it will be very sensitive to the noise. If I have a little bit of noise, I would actually have a very different optimized pen. Also, another problem is the following. If I have 2 points that are also really, really close, your minimum cost is going to be very unstable. Okay, so when you try to optimize cost functions that are very unstable, it's going to be very difficult. Okay, so because your resultant landscape will be oscillating. So the idea is to add that entropy term. So what the entropy term does is the following. I need to solve the optimization problem to compute the cost, but that optimization is actually married to Shannon entropy term. The entropy term depends on the entropy I actually assign to it. It would actually lead to more travel plan getting developed. The optimal travel plan will actually change to include more path. In this case, this is I just copied it from the internet, but it actually explains the idea. Let's say I have a probability distribution alpha and beta, and I want to find the minimum cost to make them identical. Okay, in the original one, I'm going to have one pen that are actually very disparate, and then it will be very unstable. As I actually introduce the entropy, they would introduce a diffusion effect that are actually not in the Euclidean space, but in the local neighborhood. So I would actually measure the difference with more and more branch, more and more edge, and then it leads to a Berry effect on the transport pen. So your loss functions are actually, depends on how much entropy loss, become more non-local. Okay, you get the idea? Okay, so why is that important? Because you actually have the entropy to overcome it. You are not actually forcing the point to be exactly matching another point. You are actually forcing it to matching it in a distributions locally. And that would actually help you overcome the noise. If you actually make the entropy too large, then you don't get any information, okay? You just get the entropy. But if you tune in, I actually want to deal with the noise here. So I think I actually did that in the previous lecture, in the seminar. So if you actually deal with a noise, and it can lead to a pattern that are actually resilient to a high frequency noise, and it will allow you to get the global pattern. Okay, so anyway, this is about it. So what I actually want to give you the idea is that there's a lot of detailed technical details. We cover the Lie group, okay, the symmetry, the algebra, and also the optimal transport. The optimal transport, I will dedicate one lecture later just to dedicate to it, because it's very important for the problem. But what I actually want to convey is the following. How you express the constraint is actually something that you can easily control, what can lead to a huge performance difference. Okay, so think about that. Sometimes the best norm you use is actually the mean square error. A lot of time it's not. Okay, so think about that. For different mechanics problem, you need to actually think about this on your own. If you want to write a paper, that could also be something that quite important. I think we have 20 minutes left, so the time is a little bit stretched. So the rest of the time, I would just ask the class to I would just ask the class to open the collab, and then form a group, and then we will work on the exercise together. In the syllabus, we have the lab report. So the lab report is not just the homework, you can also do it in class. I actually found out that for my daughter's 8 years old class, they have no homework. They just finish everything in school. I think this is such a cool idea. Versus if you grow up in Asia, you don't have anything you done at school. You just listen for 8 hours and you do everything at home. and you already forget about what the instructor talked about. Anyway, so I try to, so we should start here. If you cannot finishing it, I think that's fine. We'll use the rest of the time to just do the tutorial. Okay, so can few of you form a group, and then Ming and I will go around to ask you any questions, and then with the goal of finishing the exercise, okay?